Say again? Yeah, I can upload the file. Yep. Alrighty. Okay, but I do want to show you the how you can make your own program that is relatively easy to write to get this done. Okay, so let's. Do you want me to do it, or do you guys go like, no, that we know how to do this already? Bunch of for loops, yes, but there's a bunch of for loops, and then there's a bunch of for loops. So it's just a tool. I mean, we are just okay. What I'm trying to convey is when you have something tedious to do, there's no existing tools, then you make your own tool. Okay, you can do it in C, you can do it in C++ or JavaScript or Python, whatever programming language that you're familiar with. Okay, so making a parser is difficult. Okay, so I would not suggest you going full bore and make your own parser and parse everything. So don't try to do it that way. But the other way is actually pretty easy. So I'm going to just call this checker.c. Okay, so this is not even C++. No object-oriented programming here. Okay, so what we'll do is we do a main, and then we have int pqrst. Okay, just like that. And then we have for p equals to false, p is less than 2, and then plus plus p, like so. Copy, boop, boop, boop. And then on this line, we are going to replace, I think we need a global replace, so it's a dollar sign. We replace P with Q, not G. How do I do it on the same line? Oh, the percent is the problem. So on line 1, substitute P with Q. No. All right, fine. We'll just do it the brute force way. Hmm? Then you learn how to kill a process. You just have to learn how to kill the process, then you get your command line back. You can use a second SSH session to sign in. There's always a way. There's always a way. All right. So over here, you just have to go like, okay, what are we comparing? And then you're gonna go like, but tech, there's no imply in C++ or C. Then make your own. So you can go like, okay, pound define, you know, uppercase if, lowercase if is a keyword, can't use that one. So you can use uppercase, okay, XY, and it just boils down to the negation of X or Y. Now, when you use macros like this, I would strongly recommend putting extra parentheses around things just so that you don't have to mess around with the operator priority stuff later on. All right. So with that done, we can now go back to the original stuff and just kind of copy and paste the expression here. All right. Hmm? This one? Yeah, that's implication. Yeah, but it's going to be a prefix implication, not an infix implication. There's no way to define a new operator in C++ or in C. So we also have to pound include standard io.h. Not 100% needed, but instead of using a debugger, this allows me to print stuff out. And then what we need is expression one, expression two. All right. So now we just have to express expression one. So expression one in this case is the original one. So it is an if that has a if for the first one, and then the negation of an if for the second one. And then with the first one, we have um, not P and Q implies R and S. There we go. And then with the second one, we have Q or T, Q or T. And then we have not P or R. All right. I think that looks good. Yep. All right, that's expression one. Expression two is the one that we end up with. Okay, in other words, our expression two is this mess over here. It's a little bit, longer to type, but it's not that big of a deal. So we have five things. One, two, three, four, five. Okay. So personally, I like to do things like this. Okay, that's just me. And then we backfill each one. So this is not P or not R. This is Q or T. This is P or Q. And then this one is Q or not R. And then finally, we have not R or not S. Whew, there we go. And then we can now say, if, okay, so most people would go like if EX1 equals EX2, then everything matches. Otherwise, it does not match. Okay. So let me explain why this is not a good way to do it. Okay. So we just want to see a whole bunch of good and no bad, and we're all good to go. But in C, in C++, you can probably do this if you use the bool type, BOOL. But if you don't use the bool type, this is not a good idea because EX1 is not guaranteed to be a 1 or a 0. It is guaranteed to be 0 or non-zero. 5 is a non-zero, -2 is a non-zero. So the compiler does not make that guaranteed. Now, would it actually choose a random non-zero value for true? Probably not. But can it do something like that? Yes. Just to break programs. Okay. So this is not a good way to do it. So the problem has to do with EX1 is either 0 or non-zero, but itself is not just 0 or non-zero. I take it back. Let me rephrase it. EX1 is, if it is false, it is a 0. If it's a true, it is just non-zero. But we don't know which non-zero. So the best way to do it is to coerce it back into just 0 or 1. So we just have to use a ternary expression like this to coerce everything back to 0 and 1. And everything is back to 0 and 1. So we can now compare. What? Huh? Canvas is back on? Yeah, we don't need it. We don't need it. We don't need those stinky, OMS for this class. Okay, now we're gonna run this program. But you can see it's not really super difficult to write a program like this. Okay, it's just a little bit elbow grease. It's better than having to stare at your own equation like for eternity and try to wonder, is it really the same or not, right? All right, so we're gonna go ahead and run this program. Okay, GCC dash G dash O checker.c. Wow, it actually compiles the first time. I am impressed. And it's all good. Yes. Woohoo. Then you guys go like, well, maybe you make a bug to make it print it's all good all the time. So we're gonna introduce a bug to make sure that that is not the case, right? So we just have to, before you mess up a program that was otherwise good, always back it up, right? Because otherwise you cannot get back to what it used to be. So we will take out that negation and just go like, okay, maybe tech make a mistake somewhere. Okay, GCC, and then we run checker, and now some rows are bad. Like these two are now bad. They were not bad before. Is that okay? So that didn't take too long. Okay, I have a full video recording to time myself how long it took. And did it involve any concept that you have not learned in CISP 360? I think Daniel can do this in TTP ASM. Yeah, yeah, plenty. I mean, this is just a you know 5 loops nested. It definitely has enough space. Yep. No, I think I could never fit a single sorting algorithm in. I mean, 256 bytes is not that much. Okay. Anyhow, are we good with this? All right. So that makes me curious about, using Gemini and see whether Gemini will give you the same answer. But Gemini does may not understand the notation, so you probably have to explain the notation itself first, so that it can understand what is and what is or and what is implication. So I'm not really sure, I mean, you guys can give it a try, but I think this program is the easiest way to do it. All right. So is this helping you with your homework assignment? It was due today, but since your Canvas was down, so it's not due today anymore. Hey, it's still down. I mean, what do you mean? Oh, wait, wait, wait. Oh, I'm at the wrong page. I was on the wrong page. Uh, this is going to cost Amazon. The question is how much? Huh? Yeah. All right, fine. I'll make it due on the 22nd. There we go. All right, so it is due on the 22nd, and I think that's plenty of time, sufficient. Okay. Yep. Um, maybe later. Yep. All right. So now that we are done with this explanation, I think it's good to explain it again and also to look at the tool, um, both looking at the tool like this and also to just kind of look at the expansion of all of these terms, because you can see that it's pretty structured. You basically apply De Morgan's law until you cannot apply De Morgan's law, and then you look at the last operator. If the last operator, actually, in either case, if the last operator, whether the last operator is something or not, you want to convert each side to a CNF and then you just do a FOIL, and that's it. Then you can simplify or not to simplify, because if you don't simplify, this is a CNF. It is legitimately a correct answer already. I just did the extra steps to simplify and kind of compact it a little bit. Alrighty. So with that said, we are now returning back to the counting thing. So the counting thing is right here. All right, so we got a few terms to define first. Okay, so this is me shifting back to the ongoing topic. So a trial is a single attempt to do something, typically involving choosing something. A single choice is a trial. Okay, so we'll focus on this one sentence here. So depending on what you're dealing with, a trial can have a little bit of a different meaning, but it's usually a single action that gives you a single outcome. Okay, for instance, flipping a coin is a trial. It gives you two possible outcomes, heads or tails. When you have a bag of marbles, okay, picking one marble out of the bag is a single trial. It gives you a single result, and then the possibilities in that case, or the possible outcome for that single trial, would be any ball within the bag is a potential outcome. So if you have a bag of six marbles, okay, then choosing one marble out of the bag has six possible outcomes. Okay, so that's kind of explained by the next sentence. A trial has a set of possible outcomes associated with it. Each outcome represents a possible result of a trial. Are we good so far? Okay, with these two? So now we string trials together to become experiments. So an experiment is a series, which means ordering is important, of trials where subsequent trials may be affected by an earlier one. An experiment has its own outcomes. Okay, so what does that mean? So what that means is you can have an experiment such as three flips of the same coin. Okay, so you're flipping a coin 3 times. Okay, so the possible outcomes in that case, there will be 8 possible outcomes because you can have head, 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 tail, head, tail, head, head, tail, tail, head, tail, 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 head, head, tail, head, tail, 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 head. I think I lost track. And then tail, tail, tail. I think I missed one. But anyway, you guys get the idea, right? But on the other hand, if you want to choose marbles out of a bag without replacement, then you do not count it the same way. So let's just say that you have 4 marbles in a bag. Okay, so we'll go ahead and use the text editor here to illustrate the concept. So let's say you have 4 marbles in the bag. They're labeled 1, 2, 3, and 4. Okay. So for the first trial, you can have 1, 2, 3, or 4. Okay. Any one of the 4 marbles can be the outcome of the first trial. So let's just say that you are asked to choose 2 marbles out of the bag. If you have chosen one already, then the second marble can only be 2 or 3 or 4. If you have chosen 2 in the first trial, then the second trial can only be a 1, a 3, or 4. If you have chosen 3 first, then the second trial can only be whatever is left in the bag, which means you have 1, 2, and 4 left. Yep, we're looking at permutations here. And then if you have chosen 4 to begin with, then the second trial can only have 1, 2, or 3. So that means the total number of outcome for the entire experiment of choosing 2 marbles out of a bag that has 4 marbles to begin with would be 12 because you have 1, 2, 1, 3, 1, 4, 2, 1, 2, 3, 2, 4, 3, 1, 3, 2, 3, 4, 4, 1, 4, 2, 4, 3. Those are the 12 permutations as potential outcomes. Is that okay? All right. But on the other hand, if you are allowed to put the marble that you have taken out to put it back into the bag before you choose the second marble, then you have 16 possible outcomes because that would be 4 squared. All right. So it is very important to ask the question, is it with or without replacement? Question? You cannot have duplicates. So even if you have 2 red marbles, you have to mark one as red 1, the other one as red 2. Duplicates. So you can what you need to do is to make sure that all the marbles are considered to be distinct. You can look for quote unquote duplicates, like all the red marbles to be considered the same. You can then find a way to eliminate the double counting after the fact. Just like we eliminate permutations of the same combination later on. So we still come up with all the permutations first, and then we say, oh, this permutation and that permutation are from the same combination. So we divide the number of permutations by a certain factor to get to the number of combinations. So if you want to go like, okay, there are 2 red marbles, we want to consider the 2 red marbles to be the same, we can eliminate those double counting after the fact. Yep. All right. So that is what this part is, trying to say. In general, the outcome set of an experiment is represented by omega again. Okay, so omega is used a lot. This is the second time we use omega. There will be a third one later on. All right, so general counting. Generally speaking, we are counting the number of outcomes of an experiment, so lottery, coin flips, and whatnot. So we're going to use T subscript I to represent the outcome set of trial I. So a trial set, excuse me, an outcome set of trial I simply means what are the possible outcomes for trial I. Trial I is basically we're looking at trial 0, trial 1, trial 2, and so on. So we are basically just looking down the sequence of trials and identify each the one that we call TI or trial I. So in the case where trial I does not influence trial J, where J is greater than I, which means the trials do not affect each other, which typically means it is with replacement. The outcome set of the experiment of M trials would then be T0 Cartesian product with T1, Cartesian product T2, and so on, all the way up to M minus 1. Cartesian product is used because for every element in T0 as the first actual outcome of the first trial, every F in T1 can be the possible outcome, and that's why we use a Cartesian product. Okay, is that understood? Okay, using the text example here, if it is with replacement, then this whole thing would then become something that more like this, because one can appear again in the second trial. So now you have 1, 1, 1, 2, 1, 3, 1, 4, and then you also have 2, 2, right? 2, 1, 2, 3, 2, 4, and then you have 3, 3, 3, 1, 3, 2, 3, 4, and then you also have 4, 4, and so on. So that means when you count the number of uh, permutations, it would be basically 4 squared, which is 16 in this case. So this is with replacement. So every single trial has exactly the same outcome set, 1, 2, 3, or 4. No, we are just putting the marble that you took out back into the bag. Consider flipping okay, not flipping, but throwing a dice. Okay, a dice has, let's just say we have a regular dice, 6 faces, right? So we have 1 to 6. So you throw the dice once, okay? It can be one of the 6 numbers, right? For each one of those possibility, the second time you throw the dice, you still get 1 to 6. That's basically what I mean. Yep. And there are dices with 4 faces too. Yes. For those of you who play D&D, you probably know there are dices with 4 faces, 6 faces. What is the next one up? 8. I know 20 is one too. Yep. hmm All right. So that's basically what I mean. All right. So now, when you look at if you just, so most of the time we are not really interested in the set itself, the outcome set. Most of the time we only want to know the cardinality of the outcome set. So the cardinality is easier to figure out because it's just the multiplication of the cardinality of each outcome set of the trial. So it is just a multiplication. But if the outcome sets are the same for every single trial, then you're really looking at they are really the same set, which also means once you name n to be the Cartesian, not Cartesian, the cardinality of t, then the total number of outcome for the experiment is just n to the power of m. Okay, so I can start with priming you for the birthday problem. Okay, so the birthday problem has to do with birth dates. We assume there are 365 in each year. So the question now is, if I look at a class like this, let's just say that we have 12 people in the class, okay? So I'm asking, how many ways can the birth dates arrange, okay, within this whole class? So the first person has 365 days. The second person has 365 days. The third person also has 365 days. So the total number of outcomes or possible outcomes would be 365 to the power of 12 in this case, because we have 12 people in the class. So in that particular example, 365 is n because n is the cardinality of the outcome set of each trial. Each person can choose one of the 365 days. The 12 is the m because that's the number of trials. Okay, so the birthday problem has to do with what are the chances that at least 2 people in the class share the same birth date. Okay, it doesn't sound like a really hard problem. Okay, but the chances of people having the same birth date increases in a surprising way. So we'll talk about that on Wednesday. Hopefully, Canvas will be up, but I don't need Canvas to explain that one. Yep. Well, it's up now. We don't know whether it's going to be up on Wednesday. Huh? Wednesday. Yep, Wednesday right before class. So that should provide quite a bit of time. Yes.